All right, let's begin. So sorry for the late start. We just had a few technical difficulties. Hi, welcome to week 2 of Big Think AI. And I'm your host. I'm Sohan Gauker. I'm the data science lead here at Big Think. And we're going to get started on our intro to data sci presentation. That from Zoom. Folks, feel free to drop your questions whenever you want. Question to everyone in the Zoom room right now. Can you hear me? Can someone chat yes or anything? Thank you, John Yang. All right. So similar to last time, I'm just going to go over a bit about myself, qualifications, where I've been. We're going to go over what is data science fundamentally. I'll teach you guys some basic Python commands and intersperse them with some exercises. And we'll have a Q&A. You can ask whatever you want. All right. A little bit about me. My name is Sohan Gauker. I'm currently a comp sci major here at the University of Maryland. I am also a senior, so this is my last year. But in fact, it's actually my last semester. I'll be out here by December. And in addition to my comp sci major, I am also concentrating in data science specifically, and also doing a double minor in statistics and advanced cybersecurity here at the university. A lot of fun. And additionally, I was a two-time software engineer at Capital One, and I was essentially working as a summer intern there. And I had a great time learning from my coworkers and from my managers about the technology we use there. Some examples of some of the stuff I did there. Recently, I worked on essentially adding new features to the document management system so that certain features could be automatically extracted, which used a bit of Node, React, and some RDS and Amazon Web Services. The year before that, I worked on the mobile app, so more on the Swift side and the iOS side, essentially refactoring the application into a new paradigm, which uses more of Swift than combined. In general, I am the data science lead here at Big Think AI, and I am also a pretty active web liaison in my Gemstone research team, Device. It's the same one that our other lead Phil is in, and essentially we're trying to remove racial bias from AI hiring systems. I can talk a bit more about that later. But yeah, that's just where I've been doing. So I figured I'd just give a refresher in case some of you weren't there last week. But the goal of this club is that we are going to learn about data science and ML concepts. And eventually you're going to be able to code up a project in Python that will be able to utilize the data science and ML concepts that you learn in order to solve certain problems. And additionally, we're going to encourage a lot of peer mentorship. So you'll be learning not just from the leads, which is me, Samrat, and Phil, but also from each other as well, because that's one of the best ways to get some hands-on experience. And again, totally cool if you know nothing about data software or ML. We're going to walk you every step in the way. Yeah, that's all it is. Yep. So this is just a bit of the same thing. We're just going to learn about today. Specifically, we're going to go more into data science, and specifically, this is more of like a two-part thing. So next week will also be a data science lecture. Today specifically is more going to be about specific commands that you might want to know and sort of your basic data structures that you're going to be working with. Next time, we'll be working more on the data science pipeline. So I'll take you through a data science project from start to finish that implements all the commands you're going to learn today. But don't worry about that for now. We're just going to learn about the basics today. But what is data science? So the official definition is that it is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract or extrapolate knowledge and insights from noisy, structured, and unstructured data. Additionally, it also applies knowledge from data across a broad range of application domains in order to solve a specific problem. Okay, well, like, what does any of that mean, right? So essentially, here's what I just said, broke it down. So first, we're going to be using specific data structures and databases in order to actually create structure in our data. So a lot of times when we get our data from a specific data source, say like Kaggle.com or even our own field research, it can often be very unstructured almost. And this can make it very hard to work with. So essentially what we're going to use is the power of Pandas specifically, which is a library that I will talk a little bit more about later, in order to structure the data more so that it's much easier to manipulate. Second, we're going to use a lot of inbuilt methods to clean data. So now you're probably thinking like, okay, what do you mean by cleaning, right? So when I say clean data, this goes back to what I was saying a few seconds earlier about taking that unstructured data and turning it into structured data that we can actually use and analyze. So some examples of cleaning data can be removing entries that have NA in some of the spots in the row, because we can't work with data that's not there. So part of our data cleaning is going to be handling that. Part of data cleaning can also include renaming columns in order to make it more accessible to us as programmers. And finally, it could even cleaning data could also mean dropping certain data that we already have, if it means that that data is making it hard to process the entire data set. Cleaning can encompass a lot of things, but I'll go a bit more in depth later. So it's okay if it's a little bit unclear right now. Additionally, we're going to use a lot of statistical methods to analyze the data and draw conclusions. This is where a lot of the meat and potatoes of our coding will happen per se. This is where essentially we're going to use proven statistical methods in order to analyze the data in a variety of ways. And this can take many forms. It can be checking for correlations between different metrics, checking for bias between the metrics that we calculate to make sure that they are efficient. And finally, it can be ensuring that certain correlations that we are drawing conclusions from actually check out and actually exist. Because we don't want to draw conclusions from stuff that doesn't really exist. So that's part of what we'll be doing as well. Finally, and admittedly, we will probably not get into this today, but later, we were going to use the power of machine learning algorithms to create models in order to predict results from our data. This is essentially just training a machine learning model on data we have, and then using it to predict new outcomes based on new input data that we get. Does that generally make sense to anyone? I'd like to take the time now. Does anyone have any questions? All good? All right. All right. So let's get into the basics. So this first part will be a bit of a review for those of you that were here last week. But it will be, I do want to touch upon this first, as it will be very fundamental to what we're going to do later today. So, who remembers list slicing from last week? What is your name? Anand? Nice to meet you. Could you give us a brief rundown of what you remember list slicing to be, if possible?
Yeah, so I remember that list is, so every element in list has a particular index. So when we do a list slice, we are basically taking apart all the whole of the list and we're like printing that out or taking that as the output. So we use that by using the index with the indices of the particular elements of the list.
That is perfect. Thank you. Enough? That was perfect. Thank you. So in case you couldn't hear it, list slicing is essentially when we take an array and we give it certain beginning and ending indices in order to get only a subset of the array. This is going to be very fundamental in our data cleaning methods, and this is a very quick, very easy method in order to get a contiguous set of data without having to code too many lines of code. And so for reference, here's a quick example of list indexing and slicing. Sorry. So here we have a list of 6 items and they're all food. And essentially what we are doing is that we are taking this list and we are getting a subsection that corresponds to index 2, starting at index 2, and we are ending at index 5. So this will get item 2, bacon, item 3, tomato, and item 4, ham. Now, remember what we went over last time is that we are including the first index, but discluding the last index. That's why bacon is included, is in green, but lobster, which is 5, is not included in blue. Even though we put 5 here. Does that make sense to everyone? Because I know a lot of people mess that up when they're trying to split this time. All right. So again, this is just some basic list slicing syntax. You have your list first, a square bracket. Then we are going to put the initial index inclusive and the ending index exclusive. Additionally, we have an index jump optional parameter known as step. This will indicate to us if we want to be skipping certain indices from step to step. This is something I'm going to go into a little bit more in depth, so it's okay if you don't fully understand the index jump. And this is basically our formal definition. The LST over here is a list, and the above expression will return a portion of the list from index initial to index end at a step size of index jump. All right, we're going to pause for a moment. We're going to go to a exercise, and I'm also going to answer someone from the chat. Oh, hi, someone. Side note, they're doing -1. Okay, well, I was going to go over that later, but it's fine. Okay. Overrated. Okay. Don't worry about the code down here. We will get to it later. So now we're going to do some basic list slicing. Try to make this a bit interactive, so we'll have a lot of fun. What I want to do is I want to define a list of minors. So, would any brave volunteers like to list out some minors that they are taking, or maybe just interested in, maybe something your friend is doing, you find interesting? Cool. Yeah. Chat. Underwater basket weaving, so true, Samra. Anyone else would like to share their minors? It doesn't have to be one you're doing, just anything you're thinking of. Business and oh, what was the classic mistake? I forgot those semicolons that we need for our screen. Take 2 more minors if we have any volunteers. I'm gonna try to bring them on. Oh, that was fun. One more. Second, all of them. I have an ACS they're not so yeah. You said PSY. Yeah, fine. Thank you. Okay, that's nice. Run. Run. And anything now, addition fun. Okay. So let's begin the fun part. Okay, good. All right. Let's simulate the example that we had earlier. So we have 5 very cool minors that we have right now in this list. Let's say I want to use the power of list slicing to get these middle. Would any brave volunteer like to explain how would I do? That is correct. Underwater basket weaving, business analytics, and astronomy are middle grade. Thank you so much. And your name is Brian. Brian, nice to meet you. Thank you. Okay, so as a result, we have our middle three. Let's do one more quick example. I'll fill out the map for you. Okay, let's say I want the beginning three items: African American studies, underwater basket weaving, and business analytics. How would I do? No?
Minor 0 colon 4. You want the first here?
The first three.
Oh, 0.
Yep, correct. Thank you so much. Yep, this is the first. So this notation 0 to 3 will get us the first three items. So two quick things that I want to mention before moving on. If you are doing, so we wanted the first three minus, right? 0 to 3. Notice, however, that if I exclude the first index, so I just do bracket colon 3, the program should assume it's 0. And as you can see, it will give us the exact same thing as though the 0 was here. So if in this first parameter, you don't put anything, it will assume 0. Likewise, if I do not put anything for the last parameter, so I say 3 colon and then nothing, it will assume to the end of the list. So it started at index 3 astronomy, spit out psychology, and stopped at the end of the list. Does that make sense to everyone? That's great. One more thing I'd like to quickly describe is step size. So this will essentially return the index list, but if I put in a step size, sorry, of 2, I can actually skip every other line. So as you can see, it will start at the first minor, African American Studies, is going to, but because of my step size of 2, is going to add a 2 to the current index to get the next minor. So we're at 0. This is index 0, this one. And 0 plus 2 is 2. So we'll actually go to business analytics, get right over underwater basket weaving, and get business analytics. And it'll do the same thing. 2 plus 2 is 4. Go to index 4 and spit out psychology. That is what our step size is. Does that make sense to everyone? Feel free to speak up if it doesn't. It is totally cool. I just struggle with this a lot, my first time. But in any case, one more thing is that we do our old 1, 4 example and put a negative number into the step size. What do you guys think will happen? All right, you're saying no output. Who agrees with it here? Okay, interesting. Does anyone else think that there might be a different outcome? Like reverse. Yes. So this is just something I want to show you guys. Okay. Looks like we're having a bit of an issue. Okay. So as you can see, what happened is that -1 step size will essentially just reverse the list. So it'll start from psychology and work its way down to African American Studies. Admittedly, I'm not. This can be pretty helpful if you want to reverse the list, but I just thought I'd show you guys that for fun. Yes, you're right, John Yang. It does go back. Okay, let's continue. All right, let's go to libraries. Oh wow, okay. So now that we've talked about the basics of list slicing, I want to go more in depth into the libraries that we're going to be using this semester. So first, what is a comp-sci library? A library is essentially a collection of predefined methods that are made publicly available to anyone for them to download. Anyone can download them. And essentially the main reason that you would get these libraries is that it allows you to quickly reuse certain functions. For example, think about the sum function. If you're summing a list in Python or any other language, right? And remember, this sum function is probably part of some other major project that has a bunch of moving parts, super complicated. You don't want to waste your precious time writing a sum function when you already know how to do that, right? Instead, what you want to do is import a math library or use a basic library and use the default sum function. This accomplishes two things. First off, like I said, it saves your precious time. You don't have to spend time writing your freaking sum function in every single program. The other main benefit is that it prevents bugs from happening in your reusable function. So for example, let's say you choose not to use libraries and you're writing your sum function, but you accidentally put something like, say, -1 instead of +1. Now, all of a sudden, that sum function is not going to work, and it will spit out the wrong answer. However, the problem is if you're using it in conjunction with a bunch of other functions, a bunch of classes, and a bunch of other models, which you will probably be doing later in your career, it can get very tedious in order to figure out where exactly the error is coming from. So having the ability to just reference methods and you just know that they're correct, that's very powerful. And it allows us to save a lot of time and a lot of threads, which is very good. So here are the three main important libraries. The first one, which I talked a little bit about already, is something called Panda. This one down here. You don't have to memorize the logo, it's fine. The main thing that Pandas gives us is it gives us the power of this thing called a data frame. And this is something I'm going to go a bit more into on the next slide. But these are essentially very powerful data structures that allows us to very quickly organize our data. And what this in turn allows us to do is allows us to quickly execute multiple operations for manipulating these numerical tables along with time series data as well. So basically, not only does it structure the data, but Pandas is also nice enough to provide us with some basic operations that we can use to manipulate and analyze data per se. And this essentially will allow our data science journey to go much quicker, because we don't have to worry about a bunch of lists, a bunch of grades, all that stuff. Next library is NumPy. So NumPy is essentially kind of like a more complicated version of Pandas. It is Pandas' more high-key brother, essentially. Essentially, the main thing NumPy gives us is the powerful NumPy array. This is essentially like a regular list, but because it is made in NumPy and made very specially, it is very heavily optimized on the lower machine level. And all that means is that it is much easier to run very complex, very powerful computations on these special NumPy arrays. So essentially what NumPy is doing is that it's giving us access to this very special data type, and it supports large multi-dimensional arrays. It also has a lot of mathematical functions that we can use to manipulate these arrays, which we always love. And so that's something we will take extensive advantage of. There's one final one that I would like to point out. Unfortunately, it will think the screen is not large enough. It will get cut off. But go figure, that's just life. It's called matplotlib. Matplotlib is less data focused and more graphic focused. It essentially allows us to take NumPy arrays or even Pandas data frames at some points. And what it allows us to do is graph this data into various subplots and very easily manipulate the subplots. And this allows us to visualize our data, which is one of the most important parts of the data science pipeline. We can sit here analyzing the data with the most complex algorithms in demand, but if the average person can't understand what you're analyzing, then it's kind of for nothing. So essentially, to summarize, this one gives us the data frames and allows us to organize data. This one gives us very special arrays and lots of math functions. And matplotlib is the one that gives us our graphing. All right, let's dive a bit more to those NumPy arrays that I kept talking about. So, like I said, the NumPy array is a high performance version of the usual list that we've been using so far. And essentially, this is what we are going to use to build our data frames on top of. So here's a very quick, very basic example. This is how you would instantiate a NumPy array. We do NP. This is actually calling the library that I was talking about earlier. So call the library. We dot array, which instantiates our array. And in order to instantiate it, we can just add a regular Python 1, 2, 3. Now, on our side, nothing really changes. It goes from a list that says has 1, 2, 3 in it to an array that has 1, 2, 3. Nothing really changes for us. The magic that happens is more on the back, specifically on the memory. The NumPy as a library will reorganize the data contained within the list. And this is actually like a visual representation of that fact. But the main thing is that by reorganizing how the data is organized, NumPy is then able to recalculate and do a lot more special things with the data than we could normally. Does that make sense to everyone? All right. Next thing I want to talk about is the shape of arrays. So when I was discussing NumPy earlier, I did mention something about multi-dimensional arrays. All that means is that the arrays that we will be making from this point forward will essentially go in different directions and be able to encompass area and volume. And in case I was confused, here's an example. So first off, let's start with our usual 1D array. So this is just a list. It has 7, 2, 9, and 10. This is just your normal list. It has 1 axis. From before this point, this is what we have been working with the whole time. A one-dimensional normal list. Now we are evolving into our 2D array, or 2-dimensional list. So this list, as you can see, spans 2 axes, 0 axes, and 1 axis. On the back end, this is often implemented as an array of arrays. And out of curiosity, does anyone here know Java? Right. So in Java, if you want to represent a 2D array like so, you would need to make an array of arrays. So that's essentially what's happening here in NumPy. It's the same concept, basically, except NumPy does it in a much cleaner way. One thing I'd also like to point out is this shape. So shape will become very important in NumPy, as shape is essentially dictating what the dimensions of your array are going to be. Sorry. And this will become very important as in NumPy, when you are feeding your data into the various methods that we're going to use for statistical analysis, they need to be of the correct dimensionality. So for example, this 2D array that we are seeing right here, this is a 2 by 3 array. What this means, we have 2 rows and 3 columns. So the first number is dictating the number of rows. The second number is dictating the number of columns. Is that clear to everyone? Because I know I messed that up when I was representing this. Yes, we have the number of rows and then the number of columns. Good. So like I was saying, getting the dimensionality right is super important to NumPy, as there are certain methods that may accidentally reshape our data. And then if we were to try to use statistical methods on them, it might not work. So for example, this is 6 items, 2 by 3 array. If we were to accidentally reshape this as a 6 by 1 array, i.e. Something with 6 rows and 1 column, there might be a lot of methods that we might try that may no longer work. And that's obviously very not good. I wouldn't worry too much about this. We just put this on here so you guys would know what a 3D array looks like. So as you can see, it's dimensionalized, or rather visualized as a rectangular prism. You got our 0th axis, first axis, second axis now, and it's a 4x3x2. And that's what it is. If you don't really understand this one, it's fine. Most data sets that we will be working with will be 2D, so it's all good. Also, one thing I'd like to point out, if you recall correctly, I have kept saying 0th axis, first axis, and this is because we are in the comp sci realm, so everything is 0 indexed, just like lists. So I'm sure you're normally used to hearing your first and second axis, no more. For NumPy arrays, you start with the 0th axis, and then your next array is the first. Just wanted to point that out. Great deal. All right. So this is what's up.
I had done it previous slide. So in the 1D array, you have to shape 4 comma. So with that, shouldn't be like 4 columns and one, sorry, 4 rows and single column. Because it's represented as 4 columns and single row. Shouldn't it be like 4 rows and single column? The 1D.
I see what you're saying. That is a very good point, and thank you for bringing that up, because I think that is a very important thing that I'd like to point out. Yes, you would normally be correct, but if I remember correctly, I believe NumPy has a very special what's the word? Well, NumPy has a very special way of doing things, where when you have a one-dimensional array, it will denote it by stating the number of items in the array and then just the column. And then that is simply how it is represented. Yes, you are correct. This is technically denoting, it should be like this. I do see what you're saying, but I'm assuming that this image is simply not represented by that, as NumPy simply has a special way of doing things. Yep. So does that make sense? Yeah. I just wanted to be sure. So moving on. This is the shape method. Very simple. It just gets the shape of the array. This is what I was talking about. It's very useful for when dealing with a very large multi-dimensional array. So when you got arrays of 3 dimensions, 4 dimensions, 5 dimensions, very hard to visualize. So this method will help you out immensely. So as you can see, we're defining A. Anyway, we're defining A to be an NP dot array. We're defining it by a list of lists, and then we are calling A dot shape, and then it's returning the shape 3, 2. Because we have 3, this is represented by 3 rows and 2 columns. All right, so we're going to take a small exercise break up the not the slides. So do some. Okay, so let's define our first NumPy array. First. Would anyone like to explain how we define our NumPy arrays? Not going to do it myself. Yeah, that's good. Good. Thank you. And your name is? Suhan. Thank you. That, yes, that is exactly how we define NP arrays. So I will define. Do the opposite. Right. Someone shout out a number. 10. That one. More numbers. 6. 4. 3. All right, that should be good. Okay. I am about to call first our dot shape, just like we saw in the example. Would anyone like to take a guess as to what the shape of this array should be? Common three. All right, let's see. You are correct. Yep, that is correct. Yes, it is 2, 3, because this is represented as being 2 rows with 3 columns. The shape is pretty big with NP, so does that make sense? Okay, that's great. Let's try one more. Would anyone like to guess what the shape of this array is? Who agrees with 4 columns? Okay, interesting. Do you think it's comma 4? Interesting. Who agrees with comma 4? Interesting. Let's see what happens. It is 1 comma 4. So I'll quickly explain this. Yeah, this was kind of a curveball that I feel like, guys, but it's all good. So essentially what's happening here is this is represented by 1 row and 4 columns. The reason it's not 4 comma or comma 4, like we said earlier, is that when you have the shape and you're saying 4 comma 4, what you're essentially representing is a 1-dimensional array, which would be something like this would be something in the realm of 4 comma 4, 4 comma 4. This would be a 1-dimensional. By adding extra brackets here, you're denoting to the program that this is a 2-dimensional NumPy array. The only condition being you did not give it multiple arrays within the array like we did on the keyboard. Does that make sense to everyone? Why this is why this is still 2-dimensional, even though we are missing this? All right. I will now show some other pretty cool. So we have our pretty cool function you might want to know is sum. So sum in its entirety, if you just run sum on the array alone, it is going to sum every single it's going to sum every single element in the array from both lists. So we'll do 10 plus 1 plus 5, plus 6 plus 4 plus 3, which should give us 29. I would also like to introduce the concept of the axis. All right. Here's what this happens. So, you guys remember when I was talking about the axes earlier about how we have a 0 and the first axis with two-dimensional arrays? All right, good. So that's going to come into play. So by summoning the parameter axis equals 0, what I'm essentially doing is I'm telling the computer, hey, instead of doing your normal summing procedure where you just take everything and combine it, I want you to sum across a specific axis. So in the case of, so we have this. In the case of the 0th axis, when axis equals 0, we are summing. No, yeah, it is summing. Okay, we are summing across the columns. I don't know if you guys will be able to see this, and I apologize in advance if you're not. Can you guys see this? Yep. Okay, that's great. So along here is axis equals 0. Essentially, what's happening is that when we summon axis equals 0, we are telling the program sum like this. So sum these two, sum these two, and sum these two. This is why we get 16, 5, and try moving the camera. Honestly, I'm sorry, Samra, I do not quite know how to do that. But for those of you in Zoom, what we're essentially doing with the axis equals 0 argument is we are taking the first element of this list, the first element of this list, summing them, second element, summing them, and so on, which gives us 16, 5, 8. So here's a quick little exercise, guys. I am now going to try the opposite. Summing with axis equals 1. Considering that this is our original array, what should this spit out? Give you guys a moment to ponder. Exactly, 16 and 13. We'll start writing on the board again. Just like it said. I'm sorry, what is your name again? Just like Suhan said. One. Now that we set the axis to 1, we are summing in the opposite direction. Instead of summoning these columns, we are going to sum the rows. We're going to do 10 plus 1 plus 5 and 6 plus 4 plus 6. And to those of you who yep, exactly, sum. Just like I was saying, sum axis 0 sums everything up column wise. Sum axis 1 will sum up everything in row wise. For those of you in the viewing room, if you do axis equals 1, like we did down here, we will sum 10, 1, and 5, and then we will sum 6, 4, and 3. Another important function that will probably help you guys greatly when you get to the statistical analysis portion is mean. Very similar to sum, but it does exactly what it says on the tin. Instead of summing all the values, you are going to take the average of all the values. So here, I did not specify an axis. I did not give it anything. So just like this example up here, it is going to take all 6 of these entries, or it's not going to care about the columns. It's going to take everything, match them together, and produce the output. Yes. So to everyone, yep, this is probably how you want to visualize it. If, each of these inner arrays being a undefined axes return an array of their bounding sections, right? Okay, so John asks a very interesting question. So what happens if I put in an axis that does not apply? So for example, as I said earlier, axis equals 2 would represent the third dimension if we were working with a three-dimensional. However, this is not a three-dimensional array. We don't have that many dimensions. So let's see what happens. All right, so as you guys can see, we get an axis error. It will give us some stack overflow, and it will say that specifically axis 2 is out of bounds for an array of dimension 2. Now, don't get confused, because you might go, wait a minute, I put in axis 2, but the dimensionality is 2, so what's going on? Would anyone like to explain what's happening here? Yes.
Well, if CSC's coverage starts with 0, so access to that.
Yes, exactly. Couldn't have said it better myself. And your name is
Catherine.
Catherine. Thank you, Catherine. Yes. Even though this number and this number are equal, it's still not going to work because we count from 0. So something of dimension 2 can only take 0 or 1 as the argument. So just as a quick demonstration, axis 0, we are going to take the mean on the column, just like we took the sum earlier. And we get 8, 2.54. One quick thing about NumPy that I would like to note, by some miracle, we actually got whole numbers for some of our means. You're probably wondering, okay, if it's a whole number, what is the point of this decimal? What is it doing here? That's because, if I remember correctly, all the values when making NP arrays and making NP results are technically floats, not integers. And what I'm trying to say is that they're decimal numbers. They're not whole numbers. So when it gets a whole number, it's supposed to say 8.0, but what NumPy does is it's like, I'm not going to display the 0 because you know what that means. So it drops the 0 and just says 8 point. So if you see that point, all it's saying is that it's supposed to be like 8.0 in this. Does that make sense? Want to make sure no one is confused. All right. Finally, we're try it. 1. And yep, it's a similar thing. You're just going to take the average on the row side this time. Okay. So I think that'd be good. Now, let's move a little bit away from NumPy and a little bit towards pandas. So like I said earlier, pandas is the library that's going to give us our powerful data frame object and allow us to structure our data. So right now, I'm going to go a bit more into data frames specifically and like what they are, what you do. So this thing on the left is a pandas data frame. It is defined as a 2-dimensional labeled data structure with columns of potentially different types. It is very similar to an Excel spreadsheet, which is probably the first thing. So I'm going to break this down. So 2-dimensional, this means it's just like our NP array from earlier. It's got 2 dimensions. We've got our axis 0 and our axis 1. We are not working in 3 dimensions, just 2. It also mentioned something about being a labeled data structure, but don't let that throw you off. This is actually a bit unique to the NP array. So unlike the NP array from earlier, it was just a bunch of numbers. Here we have our data, but each row and column is labeled. In this example, it's not actually that helpful if it says A, B, C, and 1, 2, 3, 4. But in the future, what you could do is actually give these columns and rows, but mainly columns, very specific names. So for example, let's say you were a teacher or TA and you were grading students' midterms. Let's say each row represented 1 student, and each column represented their answer for a certain question. Instead of saying ABC, because that's very broad, very confusing to everyone, You could relabel column A as question 1. You could relabel column B as question 2 and etc. Now, not only is this very convenient for you, but the power of it is that in the future, when referencing statistical methods or any method in general, instead of having to put in column A or column B, you could then put in question 1 or question 2 if you relabel the column. This is very helpful as it not only makes our code more readable to outside viewers, but it also ensures that you are not going to make a mistake. Because it's very easy if you're coding at like 3 a.m. and you're trying to analyze some data, to like accidentally mix these columns up or something. But if you put in question 1 or question 2, with actual labels, it's much more difficult to mess up. One more thing I'd like to quickly go over is columns of potentially different types. So one thing that's actually pretty cool about pandas data frames is that the types from row to row and column to column, or mainly column to column, do not need to be the same type. So what you could do is potentially column A could be your student name of type string. Column B could maybe be their midterm average, which would be an int or a float. Maybe column C could be their seat number, which would definitely be an int. So we have like a string here, a float in this column, and an int in this column, and that's completely okay. It is completely fine to mix up your types in the data. Not mix up per se, but rather you have different types within the same data. Does that make sense to everyone? Cool. We'll go answer a pseudo question. The thing with pandas data frames is built on top of NumPy arrays. The method and each are similar to. That is so true, Samrat. It is absolutely correct. Yes, the pandas data frame is essentially like a more nice version of a NumPy. One thing that I'll quickly go over is something called a panda series, which we have on the right. And panda series is a one-dimensional labeled data structure which can hold data such as strings, integers, or even other Python codes. I'll go through this a bit quicker. This is essentially a more simple version of the data frame. Well, that was two-dimensional with columns and rows. This one just has rows, and it just has like one entry for each row. This is essentially for a different situation. If instead of like a data set, you more just have like a list of values. Like let's say you have like student averages for a midterm, and you just want to sort those averages and nothing else. You might opt for a series instead. One special thing is that you have the row numbers, and you can give them names if you want. So that can be pretty cool. We won't work with series as much, but I just thought it would be nice to point it out because some people do prefer series to data frames. We will mostly be using data frames at this level. Okay, so here are some very basic methods and properties that you can use with data frames. So just a quick reminder, the data frame is the two-dimensional one as opposed to the series, which is the one-dimensional. So I'm talking about the two-dimensional one right now. All right, first method is head. This special function will return the first n rows for the object based on the position. So the thing with the data frame is that the rows have a special order that's already preordained, essentially. And using this order and the power of the .head method, you will return the first n rows. Essentially, this is normally used in order to quickly sample a data set you've just loaded in, just to get a quick look of what the data looks like without having to load in the entire data set, which can get a bit cumbersome. By default, something like I'd like to point out is that n is set to 5. So if you put in nothing in the parentheses, you will get the first 5 rows of your data set, assuming you have 5 rows. However, if you put in another integer, like say 10, 20, or 100, you would get 10, 20, or 100 rows, respectively. And just like head, we have data frame.tail. And based on what head can do, we would like to guess what tail can do. It's the same concept, but not quite the same. Thank you. Yes. tail, unlike head, will actually return the last 10 of the data set. And just like last time, it's default to 5, so it will return the last 5 rows, but you can put in whatever number. Next, we've got data frame dot set. So what this essentially does, actually first I'll go over it. So with a data frame, you actually will have this default very special column called an index. An index is essentially just defined as a special label for rows. By default, these should be integers that go from 0 to however many rows you have. And these will act as essentially built-in row labels that you can use. But what set index lets you do, that I think is pretty neat, is it lets you set the data frame index using one or more existing columns or arrays, assuming that it is the correct. So what does that mean? Basically, when you try to sort a data frame and you try to sort it by default, it will use the data frame index, which is the row label, the default ones that Python gives. So, for example, you put in your student midterm. I'm going to keep using student midterms. It is midterm season. Hope you all are doing well. Anyways, if it's going to put in, let's say we put in all of our students and their midterm scores and all their information in the data set, but we put them in random. Python will then will take this random order and assign them row labels from 0 all the way to however many students we have. Problem is, we do a default sort, it's going to sort on that random index. So that the sort will not be helpful because since we put them in a random order, they're going to come out in a random order. So instead, what we might want to do is set the index column to something like, say, their name. So that will get rid of the default index and essentially replace it with the name being used as the row label. From there, we can do a default sort and would actually sort the students based on their name alphabetically, which is actually really useful. Next, we got dataFrame.shape. This is very similar to np.shape. It returns a tuple representing the dimensionality of the data frame. For those who are a bit confused, by dimensionality, we just mean we're going to return the dimensions. So the same way that the array we were working with earlier was 2 rows by 3 columns. In the same way, dataFrame.shape is just going to return the number of rows and the number of columns associated with the data frame. Finally, we got dataFrame.dtypes. This returns a series with the data type of each column. Now, like I said, each column in a data frame can be a different type. They don't need to all be the same. So that's essentially what this is playing at. It's giving you types that you put in. And one thing I'd like to note is that the return type is a series that I was talking about earlier. So in other words, if you're summoning D types, you're going to get something that looks like this. It's going to be like, hey, wow, okay. It's going to be like row 1. So row 1 will probably be like something like the student name. It's going to say string. Row 2 may be their midterm scores. That'll be a float probably. And row 3 may be their seat number, and that will be a name. So just like that, you're going to get a series. One very important concept that I would like to go over now is the power of grouping. So, if you guys remember from the example, when we first called something like sum on our NumPy array, all it did was just take everything and just mash it together into one big sum, which is really cool, but also like probably not that helpful. Because if we're going through all the trouble to organize the data in a 2-dimensional way, we probably want our results to be based off of those rows or columns that we took so much time to work on. In that same way, calling sum on a data frame might work some of the time, no pun intended, but it will not work all of the time. For example, this is essentially this quick data set that I have pasted onto here. Don't worry about what these are. These are just Garbo names. But anyways, let's say I wanted to take the sum of this fast column based on what the result is for the food column. If I just call my table dot sum, all it would do is sum 1, 2, 3, 4, 5, and 6 into the sum of those numbers. That's not very helpful, and that's not what I want. So instead, what we can do is use the power of grouping in order to essentially split this data set in two. Notice how this top part only has rows that have a 1 for food. This bottom part only has rows that are a 2 for food. From there, we have essentially created what would be called a group by object, which is essentially a split database. And from there, we can call sum in order to separately calculate the sum. So just to reiterate, when you're doing this group by operation, you're basically splitting your original data frame into smaller chunks, depending on the values of one or more columns. Admittedly, it's hasn't been a while. However, I do not believe it has to be this summer. Most likely, but this is definitely something that we can test. And thank you for mentioning that. That's because that is something that you would need to know before doing on statistical. But in any case, the output of this method is a data frame group by object. This is just a very special type of object that can be most readily thought of as a smaller data frame object of just every group. So just think of it as your data set, but you split it up. Group by is most useful when we use it combined with an aggregation function. An aggregation function is essentially a function that takes a bunch of data points and turns them into one thing. And an example of that is just like sum, for example, you take a bunch of numbers, you turn it into one sum. For me, you take a bunch of numbers and you turn it into one. Does that make sense to everyone?
Can we draw a parallel between a data frame and an SQL?
I don't know what SQL code would be off the top of my head, but yes, if you're asking if they are similar, the answer is yes, they are very similar. Did that answer your question? I'm going to take a chug of water, and then we're going to do some exercise. So here I have partially built out data frame. So what I am showing here is one way that we can instantiate data frames. So we call PD. That is the name of the Panda library. This is an alias I've given it to it, so I don't have to type Panda each time because that's really annoying. We're going to use dot data frame. This will allow us to instantiate a data frame. And from there, we're going to give it this dictionary. So essentially, in case we have to go over it once again, dictionaries are a special type of collection that have key value pairs. So what we're doing here is that this key is going to be our column value, or rather our column name, and the value is going to be each individual member of the column. So I first made a category. I'm actually going to rename this, so I don't like this on this list. No problem. This one is going to be food based. So yeah, no more minors, no more numbers. Okay. So someone shout out a breakfast item. What do you guys have for breakfast? That's 3. What do you guys have for lunch? Another lunch item? Nice. One more lunch item. And finally, what are y'all having for dinner? One more dinner item. So essentially what I'm just doing here is I'm building our data set correctly to make sure that we have the right calories. This is definitely not going to be accurate. On this. And now let's see what it is. So this is our data frame. As you can see, each of these entries in our dictionary corresponds to one column. I just want to make sure everyone got this because I know a lot of people normally build data frames row by row, but this is a special constructor that allows us to build it column by column. This is the category column, and we put breakfast 3 times, lunch 3 times, dinner 3 times, and that's what it looks like in the column. So this is something just another way of building your data. What's going on in that? Oftentimes the data set will be already made for you to give to you. From there, you can convert it into a data frame and perform all the operations you want on it. Samar is still correct. Yes, in just a bit of insight, when you guys do the final project, the data set will be given for you. So some of this you will not have to mention or bother with, but I know if any of you plan on taking CMS 2020 or do plan on doing just general data side work, sometimes you do have to construct your own data set. So I figured you guys should probably just know a basic way of how to do the diagram code. I represent so true. It's not running. So we have our data. We have a category, two, and calorie. We're going to try to sum it and we're going to see what happens. So you might be surprised to know that this actually won't error. Because if you remember from our last, in Python, you can sum string. The addition function essentially acts like an append, putting the 2 strings together. So what happens is that sum goes to each column and sums, or you rather, I will explain it a different way. It uses the addition operator on all of the values and turns it into one result. So 9876 is very obvious because it's just summing all the numbers. But what it's doing to do these ones is that it is actually summing all these strings together, and it's just not really just appending. So right, that's the anyways. But this isn't really that interesting or like really what we want, right? So like one thing that would be pretty cool is if we could sum the number of calories based on the category of them, like that would be pretty cool. So let's try to do that. So normally I would just start typing away and just go at it. But since I know a lot of people here are new to the data side realm and new to all of this, I would like to essentially try to do this as though I didn't know how to do this at first. So I might type in the, our data set. Let's say, I don't really know how to use group by, I don't really know how to do stuff from there. What I need to do is go to something known as the documentation of the library. And in case you guys didn't know, documentation is essentially just the not even step by step, but it is a guide of every single method in the library made by the people who made the library. It is essential for if anyone ever makes a library here in the future. And it's basically just telling other developers, hey, these are all my methods, this is what all of them do, these are some classic use cases and errors. So for this one, I'm going to search up the pandas documentation so that we can get a better idea of how to use group, assuming that I didn't really know how to do it at first. So I might try something like pandas group by right. So this is an example where it's taking group by and then it's applying the sum function. So as you can see with this documentation, it's giving us the method name, and additionally, it's giving every single parameter that we can put into it, and it's just explaining what these parameters do. It's also giving us a basic description of the function, which is really nice. So essentially, they're just saying, well, you can take one. It takes two parameters, well, two basic parameters. One is numeric only. It's a Boolean. That's what this means. And it is, if you don't put in anything, it will assume it's true. And what's essentially saying is that, hey, we're only going to use numeric. It also has another parameter called min count, which starts at 0. And it's the required number of valid values that you need to provide the operation. So let's say you have a data set, like this is like pretty cool stuff when you know what you're doing exactly. For example, if you have a data set with lots and lots of NAs that you didn't clear out earlier, you can set your min count to something like 5. And if you have a column that doesn't have at least 5 valid values, it won't sum, which is really good because sometimes you can actually get errors that would interrupt your execution, which is not good and which can interrupt everyone. Let's try using this in order to group by. So group by. Yeah, another reason we recommend using Colab is that it has auto parentheses. So this is another form of documentation that I just want to bring up to you. So this is known as an inline documentation, as opposed to our web documentation that we have first. So this is imported directly from the libraries by the people who make Google Colab, and it's essentially just telling us the same information within our own text editor. So this is essentially our description. We are going to group the data frame using a mapper. Don't worry about what a mapper is. It's just saying we're going to group data by a certain value. It also tells us for fun which parameter we're on. So here we're on the by parameter. So that's what we do. We'll do by equal. And now I may be looking at this. Well, gee, what do I put into the by? So we can read this here, and it shows us that it can be a function or a label used to determine the group for the group by. That's pretty neat. If we look at these, I want to group by this category label, so I will put in category. And now it's grouped. So let's try running this first and just see what happens. Okay. So this is our group by object. As you can see, it is not very helpful. It's just a what I assume to be a memory location. The group by object on its own is admittedly not that great, which is why we are now going to use the power of an aggregate function with it. But that's not. Now, try this. Voila, look at that. Instead of summing everything randomly, it grouped the data by the category we gave it, which is breakfast, dinner, and lunch, and then summed all the categories. Sorry, all the calories within each category. So it summed these three. Anyways, it summed these three for breakfast, these three for lunch, and these three for dinner. Pretty neat. There's also a few other aggregate functions we can do to mean. Now we'll take our averages. I am so shocked that they're all whole numbers, but you know, whatever goes. We can also do count. What this one is doing is it's actually just counting the number of entries it has for each one. We had an even split, so it's just gonna say 3. Does that make sense to everyone? Does anyone have any questions both in person or in this? Oh, okay. Okay. Okay, let's add a bit more data to our data set. Let's say our friends come over and they teach us this new pasta dish. It's very, very calorie dense. So it gives us like so many calories. You don't even know. Run that. We're gonna print out data just to make sure that it goes through. Right, so now we have this extra pasta dish. It has so many calories. Oh my god. You'll be set for life. Anyways, I want you guys to help me create a calorie sum, just like we did above up here earlier. However, instead of grouping by category this time, I want to group by food. Let's just say I want to see how the pasta calories stack up to everything. Additionally, I will actually change the lines. Okay, now we actually have. So, can you guys help me create a sum of calories of this data set based on food this time, not the category? So how do I start this out? Data down. Then group by. So we run that. We're off to a tremendous start. We have our group by object. We are actually almost done. We're just missing one critical step for summing the calories. Can anyone tell me what it is? Yep, exactly. Stop. Then. And there we go. We have now summed the data set based on the food this time. And as you can see, pasta is winning by a large margin. So yeah, might have to watch our calories. So I believe yeah, it should be done with, and now we are in our QRA. Sorry, Q and A. Does anyone have any questions? Right, right. Yeah. Right, of course. So here's the thing. It kind of doesn't. Let me explain what I mean by that. So we have three columns here, right? We have category, we have food, and we have calories. We grouped the data by the food. So what it did was it took these two waffle entries and essentially grouped them together. It took the chicken entries and put them together, the rice entries and put them together, the pasta together, right? Then it attempted to sum everything together that was not a food. So it did not sum the food column together because it was already grouped by it. This is another important point that I would like to bring up about group by. So I'd like to thank you for bringing up this question. When you group by a certain column and then try to call an aggregate function, the aggregate function will 100% of the time not apply to the food column. This doesn't really matter because we don't really take the sum of strings. But if food was a numeric column, let's say of integers, it would not sum the integers in. So anyways, since it's not using food to sum, it's gonna sum calories, which are numeric type, so it'll be like, okay, cool. It'll attempt to sum categories. However, summing is not really the same as addition, and as a result, the sum will actually fail on strings. Even though it succeeded earlier, that's why you don't see sum here. Does that make sense? Why calorie is then appearing? All right. Are there any other questions? Doesn't have to be even about this, anything. All right, anything in the Zoom chat? Because if not, I think we are good. Right? I did not. Oh, thank you. You can do that quickly. Data. Types. Yep. Properties. Yep, and this is a series. We get that the category is an object, food is an object, and calories is int 64, which is a special type of integer. The reason that it is object and not string is most likely because it's generalizing problems we saved. This is just something that pandas will do from time to time, and so don't be alarmed if you have a string object. Are we all good? All right, that marks the end of week 2. Next week, as I said, we'll be delving more into data type. Not data type, data science, but also data types. And I will be taking you guys through the data science pipeline. I have a data science project that I've already completed, and I'll just be showing you a step-by-step guide on how to complete it. I'll go very basic, so everyone will understand. And yeah, that's what we'll be doing next time. Thank you all so much for coming. I know we had some technical difficulties, but that will wrap up our session for today. Thanks again. Thanks everyone for coming, and have a wonderful day.